All right, everybody. So what we're going to look at today is section 5.3, structural induction. And you'll see here it says part one. That's important. It's definitely going to take us 2 lectures, maybe even 3 lectures to get through this section here. Okay, because in this section, we deal with what we're going to talk about today, but also we talk about trees, which you may be familiar with from other computer science classes, and I'm drawing one. I don't really know why, but there you go. There's a tree. And in order to do some proofs involving trees, of course, I have to give you some definitions, and we have to look at examples, and we have to do all that stuff. Um, and so I can't really cover structural induction and trees in the same lecture. So today we're just going to talk about structural induction, a new kind of induction for us. All right, so let's go ahead and get started. So what structural induction has to do with is it's going to be induction, but induction specifically dealing with sets that are defined recursively. Okay, so structural induction. So it's going to be induction for sets defined through recursion. All right. So it's not called like recursive induction or anything like that. It's called structural induction. And the reason it's called structural induction is because the set being defined through recursion is actually going to have a structure that can be written down concisely. And that structure is what we're going to be dealing with when we do induction. So let's go ahead and get started here. So we need to talk about recursive definitions of sets. Okay, and we should already know what recursion is. You probably have seen it in your other computer science classes. If not, we had recursively defined sequences in section 2.4. So this is what we had in section 2.4, for example. This is a recursively defined sequence. Fibonacci sequence is another recursively defined sequence. So like, ignore this definition that I've got here. I was just waving at it with my hands, and I realized that you can't see that. So in section 2.4, we did stuff like this, right? Like we said, let a1 equal 1, and then we would say, for all n greater than or equal to 1, an is square root, like 6 minus a n minus 1, right? And that was what we called a recursive definition for a sequence. And if you actually went through and you calculated the numbers, they're the numbers that we have written down here, but we'll look at them in a second. But this is how we wrote the definition, just like this. And the point is that we called it a recursive sequence, but we didn't have any other notation about it. Okay, so we just called this, at 2.4, we had this, and we called it a recursive sequence, or a recursively defined sequence. I'll just say recursive sequence because it's less writing. Right. Also in homework 2, 3, I don't know. In one of the programming assignments, you plotted one of these things. Okay. What we're going to do now is we're going to split that recursive sequence into 2 steps. And we're going to call one the basis step and one the recursive step, which you can see right here. So like the basis step is a1 equals 1, and the recursive step is for n greater than 1, an is this. Also, I realize I made a little typo here. There we go. For n greater than 1, an follows this formula, right? And the only thing that you need to really get across here is that we're calling this the basis step, and we're calling this the recursive step. And then the result is that you can calculate all of these a's, right? Like the first one is given, a1 is 1, because it says so. And then after that, for like a2, a3, a4, in order to calculate a2, you need to know what a1 is. So you plug in the 1 for a1, and you get this, square root of 5, which is this. Then once you have this number for a2, a3 is square root 6 minus a2. a2 is the previously calculated number, so you put that in right here, calculate this, you get a new number, and so on, right? And so that's a recursive definition, right? Recursive means that the formula depends on itself, okay? But sequences are not the only things that can be defined recursively. There are other things that can be. Sets can be, as well as these things, graphs, trees, polygons. We're not really going to be dealing with polygons today, but there are other things that can be defined recursively. And the basic idea behind a recursive definition is that you do a basis step where you give the smallest or most basic object in the set. So like in this example, a1 equals 1, that's where you start. a1 is 1. And then you're going to have a basis step that, you're going to have a recursive step which tells you how to make all of the other things that are in the set. And so this recursive step tells you how to calculate all of the other things in the sequence in this case. But other things are not sequences, but they still have this kind of idea. All right. So it's kind of basis step is the smallest thing in the set. Recursive step is how to make new things, right? So basis is where you basically list the smallest things in the set. And then you're going to have a recursive step. And in the recursive step, what you're going to do is you're going to tell us how to make new things in the set, how to get bigger things in the set, I'll say. Not necessarily bigger in terms of numbers, right? But just more complicated things. Bigger things in the set from smaller things in the set. And again, bigger and smaller don't really have a lot of meaning here. I'm just using those words because often that's the case. Okay. And so that idea is going to tell us how to come up with recursive definitions of things. So, um, I mean, I've got an example here, and this is actually the entire thing is written down, but just pretend you don't read this right now. I just scribble it out. Now you can't read it. So let's think about this. So example, we're coming up with a recursive definition of a set S containing positive multiples of 3. Okay, what is that? Well, if you write down the set looks like this. So the set contains the positive multiples of 3. So S is, well, what's the smallest positive multiple of 3? It's 3. What's the next multiple of 3? 6. What's the next multiple of 3? 9. What's the next multiple of 3? 12, right? And then that just keeps going, and that's the set S. Okay, and there's a lot of ways that you can actually define this set. You could do it in set builders notation. I'll do it in set builders. That's not what we're supposed to be doing, but I'll do it. Set builders notation. You could say that S is the set of all X, where actually, better yet, S is the set of all 3n, such that n is an integer, positive integer. Right? Wouldn't that give me all of the positive multiples of 3? It would, right? So this right here, this is a definition of the set, but it's not a recursive definition, because recursive definition requires you to tell us how to make the bigger things in the set from the smaller things in the set. And so another way to define this, I mean, it's written right here, but I will do it from scratch, is this. So we could say for your basis step, you just want to give like the minimum number of things that you actually have to list, because you can't give a formula for it. So what's the smallest thing in the set S, right? The smallest thing in the set S is a 3. So you would say basis step, 3 is in set S. Okay? So you just list off basically one of them. Sometimes you need two, but you list off something in the set. And then what we need for the recursive step is a rule, and the rule is supposed to tell you how to come up with new things in the set, provided you have something already in the set. So assume you have something in the set. So you say, if, let's say A is in S, or X. If X is in S, so I'm using the exists in symbol. So if X is in S, how would I get something else that's in S? And so think about this. If you're starting from 3, how would you get something else in the set? Like, how do you get from 3 to 6? From 3 to 6, you add 3. That's what I would notice. From 3 to 6, you add 3. From 6 to 9, you add 3. From 9 to 12, you add 3. So you just keep adding 3, and that will get you all of these, right? So I say, if X is in S, then X plus 3 is in S. And I think that'll do it, right? Because think about how this set works. So S is, according to the basis step, right? According to the basis step, 3 is in S. So if I'm writing down the set, I say, aha, 3 is in S. And then once I do that, I look at my recursive step. And my recursive step says, if X is in S, then X plus 3 is in S. So just imagine putting a 3 right here. Well, 3 is in S. So 3 plus 3 is in S, right? So that would mean 6 is in S. Well, now you've got two things in the set. So you go back to the beginning and you say, well, now I've got 3 and 6. But if you put a 6 in there, and then you can put a 6 in there, if 6 is in S, then 6 plus 3 must be in S. So that's a 9. 6 plus 3 is 9. And so on, right? Every time you get something new, you can take that something new and you could put it right there. And for both of the X's. And 9 is in S, so 9 plus 3 is in S. So you get 12, right? So you keep applying this rule repeatedly, and that's how you're going to get everything that's in the set S. Okay? And that's how you come up with a recursive definition of a set, right? So what you can see here from the two definitions that I highlighted, the green one and the yellow one here, here and here, is that you can have a non-recursive definition of the set, or you can have a recursive definition of the set, and you use whichever one is more convenient for whatever you're doing. Okay. Now let's see if we can identify what set we're talking about from this next example. So on this next example that we have here, so I want to, it says what elements are in the set T, and then I give you the definition. Okay, so in order to do this, we're going to do exactly what we started doing here, where we're just writing out a set. So what elements are in T? So you start out by saying T is, okay, now let's just start putting stuff in T. And this is really a lot easier than it seems like it is. Okay, so basis step 1 is in T. So what do we do? Well, you just do that. 1 is in t. Okay, now then what you want to do is you want to look at the rule, and the rule in the recursive step tells you how to get new things that are in t. So what's the recursive step say? So if n is in t, n plus 1 is in t, and n minus 1 is in t. And so there's actually two rules. And you can have two rules, that's fine. It's just telling you there's more than one different way to get something new in the set. So just think about putting a 1 in for both of the n's here, right? Like, because right now, if n is in t, well, the only thing we know that is in t is 1. So 1 is in t. So put a 1 there, and also put a 1 there, and say, well, what are we going to get if we put a 1 in both of those n's? This one says n plus 1 is in t. N plus 1. So if n is 1, we have 1 plus 1, which is 2, is in t. So like this rule, right? This rule right here is going to tell me that 2 has to be in t. Okay. What about the other rule? We got another rule. The other rule says n minus 1 is in t. So if you put a 1 in there, you have 1 minus 1 in t. So 1 minus 1 is 0. So 0 is in t. All right. Now, once you do that, you say, okay, well, now I've got 3 things in t. So you have to take these rules, and you have to apply the rules to 2, and you have to apply the rules to 0, right? You just keep applying the rule until you know what the set looks like. So once we've done this, we just erase this, erase this, erase this, and say, okay, well, now we've got this 2. So put a 2 in there and put a 2 in there. What are we going to get? According to the rules, 2 plus 1 is going to be in t. 2 plus 1 is 3. So we get 3. And then according to this rule, 2 minus 1 is in t. 2 minus 1 is 1, right? So 1 is in t. But this is a set. You don't have to list things more than once. So 1 is in t, but we already knew that 1 is in t, so you don't actually have to write this. So just erase it. Okay, so that's for 2. That's for 2. What about 0 now? So think about putting a 0 in for both of these. So erase, erase, put a 0 in, put a 0 in. Okay, so what will that give us? Well, 0 plus 1 is in t. 0 plus 1 is 1. Again, we already have a 1. Don't have to worry about that. What about this? 0 minus 1 is in t. 0 minus 1 is minus 1. So that's new. So put a minus 1 in there. All right, so we got a minus 1. So we've looked at this, this, and this. Now we're on to the 3. Put a 3 in for both of these. What will that give us? I have a software update? Oh no. All right, well, get out of the way, software update, so I can finish. All right, put a 3, put a 3. So if we put a 3 in, what are we going to get? Well, 3 plus 1, that's going to be 4. That's new. Put a 3 in here. 3 minus 1 is 2, but we've already got 2 written down, so we don't need to write it again. So all we get is this 4. All right, that's it. So then move on, get rid of the 3's. What's after 3? We have minus 1. To put a minus 1 in for both of those rules, what will we get? We will get minus 1 plus 1 is 0. We've already got a 0. Minus 1 is going to be minus 2. Like that. And then we continue on in this fashion. And so I'm not going to keep going. But what you should be able to see, and it's not always, you're not always going to get there right away. But what you should be able to see after a while is what's going to happen is we're getting like 1, 2, 3, 4. we're going to get a 5, right? Because if you take this 4 and you put it in here, you're going to get 4 plus 1 is 5. Okay. And then also we've got negative numbers, it looks like. Well, we have 0, first of all, 2. But then we have -1, -2. We're going to have a -3 eventually, right? Because if you take -2 and you put it in here, you're going to have -2 minus 1, which is going to be -3. So you're going to have -3. So actually look at what's happening. You're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also, you have 0, -1, -2, -3, -4, all the way down, right? So if you actually look at what's going to actually be in this set, what's actually going to be in the set is going to be all of the positive integers and all of the negative integers and 0, right? It's going to go ... -3, -2, -1, 0, 1, 2, 3, ... It's actually just all of the integers. And if you think about it, once you're a little bit better at these, that's obvious, right? Because think about it. We're starting with an integer. And if you add 1, you get another thing in the set. So we're starting at 1, and then we're allowed to add 1. So from 1, you can add 1 and get 2. You can add 1 and get 3. You can add 1 and get 4, 5, 6, 7. So this is going to count up. And you're allowed to subtract 1. So if you start with 1 and start subtracting, right, you go from 1 to 0, from 0 to -1, -1 to -2, and so on. So this is going to make you count up starting at 1, and this is going to make you start counting down starting at 1. And of course, that ends up with everything because you're counting up by ones and counting down by ones. All right, so that's that. Let's see if we can do another one. So let's look at this. So how would we come up with this set? And so I told you that they're powers of 3. And so what you want to think about is they're powers of 3, right? So they're 3 to the 1, actually 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, ... That's true, but we're thinking about this in a recursive way, which means not what are they individually, like I have written here, but how do you get 1 assuming you already know one of them? Like if you already have a 1, how are you going to get a 3? Right? And you could think, well, based on what we saw up here, right? We were doing like n plus 1 was going to go 1, 2, 3, 4. And here we had x plus 3, which was going to go 3, 6, 9, 12, count up by 3s. And so you might think it's the same thing here, where you say from 1 to 3, you're adding a 2. From 3 to 9, you're adding a 6. From 9 to 27, you're adding a 18, right? But when you look at those numbers, like that's not one rule. Like add 2, add 6, add 18. I don't know what rule that is. I don't like that. So you don't want to think about it, this one, as adding numbers. That's not the right way to think about it. It won't give you the formula. So what you want to think about instead is for powers of 3, the formula, the rule is that you're multiplying, right? To get from 1 to 3, you multiply by 3. To get from 3 to 9, you multiply by 3. To get from 9 to 27, you multiply by 3. Right? So do you see that? You come up with that idea that if you know one thing in the list, you get the next thing by multiplying by 3. So you get from one thing in the list, one number in the list, to the next by multiplying by 3. right? As soon as you have that idea, really you're done with the problem, because what this problem is asking you to do is to write out a recursive definition. And so your recursive definition is, give me the first thing in the set. So the first thing in the set is a 1. So you just say 1 is in, well, what are we going to call the set? Needs a name. Doesn't matter, just call it like S. That's fine. So you're going to start with a 1. And for the recursive step, I already know the rule. The rule was you get from one number to the next by multiplying by 3. So what you say is, if x is in S, then 3 times x is in S. And that's it. Because 1 is in S, so 1 times 3 is in S, so now you've got 3. But then 3 times 3 is in S, so you got 9, right? So if you list them, 1 is in S, multiply by 3, you get 3. But then 3 times 3 is in there, so you get 9. But then 3 times 9 is in there by this rule, so you get 27. But then 27 times 3 is in there, so you get 81. Right? And so that's it. So as soon as you came up with this idea that you get from one number to the next by multiplying by 3, that was all of the hard work. After that, you just write it down. Okay, so these are not as hard as they're going to, initially seem. They're not that bad. This chair makes a lot of noise. Okay, so next thing I want to talk about is just something that they just kind of throw at you in the homework, and it's a modular arithmetic, and I want you to know what it is, so we're going to talk about it. Okay, so this is what modular arithmetic is. So first of all, the notation. We say A is congruent, or you could say equal. A lot of times people will say equal. A is congruent to B modulo in. This right here is how you say in words this right here. And it says, if both A and B have the same remainder when divided by n, assuming A and B are positive. Okay. There's other ways to define it, but we're not using negative numbers, and so this is going to work for us. This is going to be for positive numbers only, but this rule will work. Okay, and so I've got some examples here that are written out, but I kind of don't want to use them yet. Let me scroll down to the end here. Come on. I think I need to, if I write here, then I think it'll let me scroll. Aha, did. So I'm just using this as scratch paper here. So remember, like, this is what I said. I said A is congruent to B mod n. Sometimes you'll see parentheses, but A is congruent to B mod n if basically A over n and B over n have the same remainder, like when you divide. So example, so like what is, so I'm just going to say like compute. Like if you wanted to know what 9 mod 2 is, for example, what is 9 mod 2? So what you do is you do 9 divided by 2, right? 9 divided by 2 is 4. But what's the remainder, right? So you have to think about like elementary school math before you know how before you knew how decimals worked. What's 9 divided by 2? You'd say 2 goes into 9 4 times, right? 2 times 4, and then what's the remainder? 2 times 4 is 8, so the remainder would be 1. 2 goes into 9 4 times with remainder 1. Does that make sense? 2 goes into 9 4 times with remainder 1. So 9 over 2 is 4, remainder 1. So what is 9 mod 2? 9 mod 2 is 1. Okay, because when 9 divided by 2, the remainder is 1. The 4, we don't care about the 4. Okay, and that's how modular arithmetic works. So, like, for example, if I go, let me just think of some numbers here. Thinking's hard. Okay, like 23. What is 23 mod 5? What is that? 23 mod 5, divide by 5. So how many times does 5 go into 20, right? 5 goes into 23, sorry. 5 goes into 23 4 times, right? 4 times 5 is 20. What's the remainder? 3, right? So 23 mod 5 is 3. Also, a lot of times you're not going to see it this way. So the mod 5 here that's written, it kind of doesn't matter where it is. So 23 mod 5 is congruent to 3. A lot of times you'll see it written this way. 23 is congruent to 3, and then they'll write mod 5 at the end. So that's the same information. As long as you know that you're talking mod 5 or modulo 5, then you know what you're talking about. It doesn't matter really whether you write it at the beginning or the end, because this mod 5, like mod 5 is not an operation. It's describing the how you're doing the math. So 23 is congruent to 3 mod 5, or you could say 23 mod 5 is 3. As long as you know you're talking mod 5. Doesn't matter if you say it at the beginning or the end. You could even say mod 5, 23 is congruent to 3. Say it at the beginning. Doesn't matter. Okay. Now, so what that means is that they can ask you things like, they can say, is, 10 congruent to, 7 mod 4? Right? The answer would be no. Why is the answer no? Because, well, think about it. You divide by 4. So 10 over 4, right? 10 divided by 4 is 2, right? 2 times 4 is 8 with remainder 2. So 10 is actually congruent to 2 mod 4. And 7, when you divide 7 by 4, 7 over 4 is 1 with remainder 3, right? So 7 is actually congruent to 3 mod 4. So 10 is congruent to 2, but 7 is congruent to 3. And so they're not congruent to each other, right? So you're just talking about the remainder when you do the division, okay? So, let's see here. Where are we? The structural induction. Okay, and then this is just some basic rules for modular arithmetic that I don't think you need to know. But what you do need to know about, I think, in order to do the homework, it looks like, is just something like this. So like, here's something that you would want to be able to do. Which positive numbers, or just, I'll say, yeah, which positive integers n are, how do they word it? Sorry, I'm just looking for where it says like the word mod in the homework. I can't really find it right away. So, which positive integers in are modulo are congruent, I'll say. To 1. You know what? I'll say it this way. I'll say it in symbols. So which positive integers in satisfy n equals 2 mod 3. Right? So first of all, you would need to understand what I'm saying there. When I say n satisfies this equation here, maybe I should write congruent, sorry. N is congruent to 2 mod 3. I'm saying that when you divide by 3, the remainder is 2, right? So when you divide by 3, the remainder is 2. That's what I'm saying. And what are those numbers? And so it's actually a pretty simple thing to write down. So the first one is if the remainder is 2, the first one is 2, right? Because 2 doesn't even go into 3. So, 2 goes into 3 0 times with remainder 2. And then what's the next number? So you divide by, the remainder is 2 when you divide by 3. It would be 5, right? 3 goes into 5 one time with the remainder 2. All right, what's the next one? So the next one with the remainder 2, well, like we're counting up by 3s basically, right? Because we're talking about dividing by 3. So like, for example, 2 times 3 is 6, right? 2 times 3 is 6, and plus 2 would be 8. And so 8 is going to be the next one because 2 goes into 8 3 times, and then the remainder is 2. And so all that's happening here is if you're talking mod 3, then that means you're counting up by 3s. And it's really that simple. So 2, 5, 8, 11, 14, 17, ... That's actually the set that we're looking at. And you can work it out, right? Like, try to divide 14 by 3. 3 goes into 14 4 times. 3 times 4 is 12. What would the remainder be? Well, 12. And so it takes 2 more to get 14. So yeah, so that works, right? It's a remainder 2. All of these are. And so just keep this in mind for a little bit, because I think we'll have a problem where we have to write down some of these. Okay. Now let's ignore what I just did for a minute, because the next example is not that. I don't know why I wrote this down here. Let's take a look at it. I said if a is congruent to 3 mod 5, then 3a plus 4 is congruent to 3 mod 5. And we're supposed to show that. I don't know why, but I've got some rules here. I think I just wanted you to become more familiar with modular arithmetic. So I guess let's just try to prove this. This is not entirely relevant for the homework or anything, but we can look at it. So like, let's say you have this, a is congruent to 3. And just think about this as it's like an algebra equation. A equals 3. But a is not 3, it's 3 when you do mod 5. So just think about this part right here as being an equation, and this is just describing the type, like what do we mean when we say equals? It's actually congruent, not equals, but basically equals. Okay, so So if you have a is congruent to 3 mod 5, and this is an equation, then how are we going to get to this? Well, let's multiply by 3, right? Because this is a and this is 3a. So let's multiply by 3. So let's look at our rules here and see if this is actually a rule. So if a is congruent to b, then ka is congruent to kb. So a normal algebra rule, right? Like if I said this, like x equals 7, you know that in algebra you're allowed to like multiply both sides by a number, right? Like I can multiply both sides by 2. So like if I had x equals 7, you multiply both sides by 2, and you get a new equation, 2x equals 14. That's allowed, right? You're allowed to multiply both sides by a constant. Well, that's what we're talking about here. This rule is saying if you have a congruence, you can multiply both sides by a constant. So if a is 3 and I want 3a, multiply both sides by 3. So just multiply both sides by 3. So you get 3a, and then multiply 3 by 3, and you get 9. And that, again, we're still looking mod 5. Right? But here's the thing. So I just multiplied both sides by 3. That was allowed. But if I want, you don't have to. And in fact, I'm not going to after I say it, but I'm going to tell you you can do it. You've got a 9 here, right? Well, what is 9 mod 5? Right? If you divide the 9 by 5, 5 goes into 9 one time. What's the remainder? It's 4, right? Right, like 9 is actually 4 when you work mod 5. Right? So if I wanted to, I would be allowed to erase this and just put a 4 there. Because 4 and 9 are actually the same number when you're doing mod 5. But let's just leave it 9. So I just multiply by 3 on both sides, and I have 3a congruent to 9. Now this says 3a plus 4. So I need to add 4. And I look at my rules, and this rule right here says if a is b, a equals b. Reading it as equals because it makes more sense that way. But if a equals b, then a plus k equals b plus k. So I'm saying you can add a number to both sides. So if I want a 4 there, I can just add 4 to both sides. So we just go plus 4 plus 4. So on the left-hand side, what are we going to get? We get 3a plus 4. So that's 3a plus 4. On the right-hand side, you've got 9 plus 4. What's 9 plus 4? It's 13. 13 mod 5. Now, at some point, you do actually want to figure out what 13 is mod 5. I could have done it at a previous step. I'm going to do it now. What's 13 mod 5? So 5 goes into 13, right? 5 into 13 is 2 with what's the remainder? Remainder 3, right? So 3a plus 4 is actually congruent to 3 mod 5. And that's what I was supposed to show. And so what was the point of this? The point of this was just, I was trying to help you understand that if you write something like this, it looks like an equation. It looks like a equals 3. And actually, it follows a lot of the same rules. Like you can multiply both sides by a constant, which we did. You could add a number to both sides, which we did. And then you can simplify. If you have any whole numbers, you can actually simplify them mod 5, now that you know what mod 5 means. Remainder when you divide by 5. So 5 goes into 13 twice with remainder 3. So 13 is congruent to 3 mod 5. And so that's just to help you hopefully understand what modular arithmetic is trying to talk about. Okay, so that's modular arithmetic. All right, now let's actually talk about structural induction, which of course is what the section is called. Structural induction. So structural induction is actually structural induction is, I think, the easiest type of induction. Proofs are very short, I think. So let's look at this. So there's a method of induction you can apply to any sets that are defined recursively, structural induction. So you've got a property that you want to show, and you want to show that everything in the set has the property. So what you do is it's a two-step process, just like induction usually is. So you show that P holds for every LL element of S defined in the basis step. That's the equivalent of your basis step of a normal induction proof. Then you assume if P holds for the elements that are used to make new elements, then P must also hold for the new element. Okay. So that is complicated sounding. It is not complicated to do. It's complicated sounding. So what do I want? Well, let's just do the examples. I was going to come up with something else, but let's just do these examples. All right. So I think that what we're going to do is look at a set, and then after we have a set, then we're going to do a proof. So don't be confused, right? There's we talked about recursive sets in this section, and now we're talking about structural induction. And structural induction is for a recursive set. Right? So that those are two separate problem types. Like some problem types are going to have you write out like recursive sets or write a definition, and some problems are going to have you perform induction. Separate problem types. Okay, so A and B here are separate problem types on this example. All right, let's look at this example, in fact. So let S be defined as follows. Basis step, recursive step, write out 4 terms. Okay, what is this S? Right? So what is S? All right, basis step. 3 is an S. Okay, 3. All right, next thing. If n is an S, then 3n plus 4 is an S. Okay, so we need to start using this formula to calculate new things. So you know how to do this, right? We put our first element is a 3, so put a 3 in here. What are we going to get? 3 times 3 is 9, and 9 plus 4 is 13. So the next thing is 13. All right, next thing. Well, now you have a 13 here. So you're going to take a 13 and put a 13 in for the n. So what's that going to be? 13 times 3 plus 4 is 43. That's the next one. Okay, once you have 43, you're going to put a 43 in here for n. What's the next thing? 3 times 43 plus 4. 133. Okay, what's the next one? 133 times 3 plus 4. 403. Okay, dot, dot, dot. Okay, so this is the set S that we're talking about. Okay, so that's everything looks like that. 3, 13, 43, 133, 403. And we don't need to know a lot about it. I mean, you can see that they all end in the number 3. We can notice that. And now let's actually try to do a proof involving this. So what are we supposed to prove? We're supposed to prove using structural induction that every element of S is actually congruent to 3 mod 5. And so this is the property. If n is an S, then n is congruent to 3 mod 5. Okay, so what is structural induction now? So let's look at it. So structural induction, in order to do structural induction, to prove this property, you need to show that the property holds for every element of S defined in the basis step. That's the key. So your basis step for the proof is just showing the property for the basis step of the set. And what makes this confusing is there's a basis step for the set, and then there's a basis step for the proof, right? So my proof is this, proof. So I need my basis step. So what we need to do is, well, this is the property, right? That's the property P that we're talking about. So show that we need to show that the basis element of the set satisfies that property. That's what we need to do. Show the basis element of the set has the property. What's the property? The property is congruent to 3 mod 5. Okay, what's the basis element of the set? It's 3. So what we would be showing is 3 is congruent to 3 mod 5. That's what we would be showing, right? Because we're supposed to show every element of S is congruent to 3 mod 5. Well, is 3 congruent to 3 mod 5? Of course that's true, right? 3 is congruent to 3. True. So just like all induction proofs, the basis step tends to be very simple. You're just showing that the first element, typically the first element, right? However many you have, whatever you have here, whatever you have in your basis step for the set, that's how many things you have to show satisfy this property or this property, congruent to 3 mod 5. Okay, so we did it. That's the basis step. So for the induction step of this proof, this is where it's a little different than the old style induction proofs. So what you do is you assume, so you see how this is right here. Here, it says if n is an S, then 3n plus 4 is an S. So what you do is you assume that n has the property. So we need to do this. We need to assume n has the property. Now, what does that mean in this set? Assume n has the property. What's the property? The property is congruent to 3 mod 5. So assume has the property n is congruent to 3 mod 5. Now, what do we need to show? What we need to show is this has the property, 3n plus 4. So assume n has the property, n is congruent to 3 mod 5, and then we need to show, what was it? 3n plus 4 has the property. So we would need to show that 3n plus 4 is congruent to 3 mod 5. Okay, that's what we would be trying to do. Okay. We figure out how to do this. I only meant this to be scratch work here, but I think I'm going to try to copy it. Actually, just move it like this. Okay, that's good. Okay, make big. Okay. So what I wrote here is what I'm trying to do, right? This is what I'm trying to do and I have not done yet. So your induction hypothesis is this. Okay. So that's where you start. So we start with start with the induction hypothesis. So n is equal to 3, congruent to 3 mod 5. And then what we're supposed to do is we're trying to get to this. Well, that's easy, right? We know how to do that because we know that we can use normal algebra rules. So we could take this right here, and it's congruent to 3 mod 5, and we can multiply both sides by 3. Multiply it by 3. We get 3n equals 9 mod 5. Did we already do this? Is this the same one? Fine. 3n is congruent to 9 mod 5. Okay. Now, if you want, you can just write that immediately as 3n is equal to 4 mod 5, right? Because 9 divided by 5 is 1 with the remainder 4. But you don't have to do that. I'm only doing it because I think we already did this without doing that a few minutes ago. So 3n is congruent to 4 mod 5. Okay. And what do we need to do now? Well, this has got we did this. Well, now we have a 4. So add 4 to both sides, plus 4 plus 4. So you get 3n plus 4 is congruent to 4 plus 4, which is 8 mod 5. But then what is 8 mod 5? Well, again, divide. So 8 divided by 5 is 1 with remainder 3. And that is actually what we were supposed to show that 3n plus 4 is 3 mod 5. So that's it. That was the induction step. And then you can make your conclusion, which is so all elements of S, I'm just going to call it S. That's what we called it. All elements of S satisfy n is congruent to 3 mod 5. That's what we were trying to show. I think I wrote it in words. Okay. And so that is a structural induction proof. And so the structural part of it is, let me erase some of this. So for structural induction, what you do is you take this and you just show this has property P. Okay. And then the recursive step of the proof is you say if n is an S. So you say if n has property P, then this 3n plus 4 has property P. And that's structural induction when you do that. So it's not regular induction, because regular induction was like show that if it's true for n equals k, then it's true for n equals k plus 1. There's no plus 1 here, right? There's no k plus 1. It's if this has the property, then this has the property. But this is not n plus 1. It's, in this case, 3n plus 4. So it's not the same as regular induction. But the idea and the form is very similar, because you still have an assumption that something smaller has the property, which is mod 5 equals 3 mod 5. And then you have something bigger, this 3n plus 4, and you need to show that it also has the property congruent to 3 mod 5. So when you actually write down the proof, of course, it looks a lot like a regular induction proof, despite being technically a new thing that we're calling structural induction. Okay, so that was just ticked over to 1 hour just right now. So I'm going to stop this lecture here. We did one proof only. In the next lecture, I think what I'm going to do is do a couple examples from the book on structural induction, and then hopefully also talk about trees and a little bit. Okay, so that's it for now. I'll talk to you guys next time.